Hello, PreCalc. This is your Thursday edition, so that must be the 5th of January. And we're going to take vectors and actually use them in real-life problems. I'll show you two, and between tomorrow and the next day you'll be doing about 5. So, sort of like physics class again. So, here we have a gun, and from the gun is a bullet, and the bullet has a velocity vector drawn representing 1,200 feet per second, and it's shooting at 6 degrees from the horizontal. So if you would stop and make a sketch of that, sure it's in, all right? And the question is, find the components of that velocity vector. All right, we have color-coded them before, not necessary, but it helps us keep them straight. So I put in the x component. Any diagonal vector can be, any vector really, can be divided into a horizontal part, we call it component, and a vertical part. And they are drawn, the horizontal and vertical components. Now I just need to know their lengths. Because the angle is very small, are we expecting a large x component and a small y component? Are we expecting the x and y components to be about the same? Or are we expecting a small x component and a large y component? Think of what you expect. The picture will tell you. Alright, so let's do the work and see if our expectations are met. So in order to find the length of the components, we always pull out the cosine to do the horizontal part. So it's always 1,200 times the cosine of the angle. So that is, we put this on a coordinate plane. We don't have to make any adjustments for that angle because it's in the first quadrant. So we have 1,200 cosine 6. Do you remember why that's true? Hopefully you do, because this is a right triangle. If this is x and this is y, we see that the cosine of 6 degrees is adjacent over hypotenuse. Remember the basics of trig? Adjacent over hypotenuse. So I simply multiply both sides by 1,200, and I get, oh, this is x, sorry. I'm using cosine, it's always x. I got them written wrong here. X, y. All right, 2 hands up, put them down. All right, so we have cosine of 6 is adjacent, the x component over the hypotenuse 1,200, and solving for x, we get 1,200 cosine of 6 equals our x component. But I don't go through that every time. I go right to this. I always know it's the hypotenuse cosine angle for the x component. So I just want to remind you why that's true. And so 1,200 sine of 6 will give us the y component. So I put those in the calculator earlier, and I got a component of 1193 for 1,200 times cosine of 6, and 1,200 sine of 6, I got 125. So we're going to write those results in component, in vector terminology or vector symbolism. So we're going to put the x one first in the pointy parentheses, and then the y. So 1193. The x component was very long, and the y was very short comparatively. And these are in feet per second as well as the hypotenuse velocity vector. So we can write that another way, and this is the camp I'm in. We can say that this is 1,193 of these unit vectors, which we called I, plus 125j. So that show up. All right, it's good enough. All right, so this is the answer to the question. We found the components written in two different ways. Your choice. All right, the second problem is we're going to have a spot, and from this spot, let me see where I am. I'm going to move this spot over here. I think it still shows up. Here's my spot, and from that spot, I'm going to apply some forces. There's going to be a 75-pound force on that spot at 30 degrees. There's going to be a 100-pound force at 45 degrees and a 125-pound force at 120 degrees. So there are going to be three forces acting on my spot. So 75 pounds, I'm going to sketch this. 120 is about here, so that's the longest vector, it's 125. Then the 100-pound one, I'm going to draw a shorter vector to represent 100, is at 45 degrees. And then there's an even shorter one representing the 75, and that one is right here. So 75 is at 30 degrees, 45 degrees for the 100-pound force, and 120 for the 125-pound force. So I'm going to take these three vectors and find what is the resultant force of all the three forces acting on that point. What can I come up with one force on that point that will do the same that all three do? So in order to do that, I'm going to have to add those three vectors and find the magnitude and the direction of that sum. So to do that, we're adding vectors, we have to have their components. So I'm going to go ahead and draw a graph with just the 125 on it. That's at 120 degrees. So I'm going to get the components for that. So we have an x component and a blue component. So once we get the x and y components for all three forces, we'll add the x's together and the y's, and we'll have one force that will act like all three of those. So to get this, it's going to be 125 cosine 120 for the x component, 125 sine 120 for the y component. When I tap that in, I got negative, say 63, around it, and 108. So 108. So check that. So 125 sine 120 will give me the y, and that's the x. So I have a choice. I can write it with the pointy parentheses, or I can write it as i's and j's. All right. So here's my two choices for that one. All right, let's see. I will draw the other one. The next one is 100 pounds at 45. So putting in the x and y components, x, y. Let me see if that shows up. Yeah, it looks like it does. So I have 100 times, remember this was 45 degrees, so we get 100 cosine 45 and 100 sine 45. And when I did 100 cosine 45, I got 71, and same for the 100 sine 45. 45 acts that way, their sine and cosine are the same. So I get 71, comma 71 pointy box, or 71i plus 71j. All right, third one I think will go off the screen. Let me move the camera a bit. All right, the third one is going to be 75 pounds, this is off the screen, but looking at your notes, 75 pounds at 30 degrees. So I have the red component and the blue component. So 75 cosine 30 and 75 sine 30. And when I did that, I got 65 and 38 rounding. So I can write it pointy box style, or I can write I's and J's. Alright, I'd like to have all three of those in the screen. So let me see if I can mess with this to accomplish that. Alright, hopefully you can still see. Alright, so I'm going to use the I and J. So I'm going to add this, this, and this. This is my addition right here. I'm going to add all the I's to all the I's. So I'm going to get negative 63 plus 71 plus 36. And when I did that, I got 71, rounded. And then 108 plus 71 plus 38, that's the J's. I got 217, that's the J. So we would be finished and could be finished with this answer, but I really cannot visualize that very well. I'd rather go back to magnitude and angle so I know exactly what the one force will look like that will accomplish what all three of these do. So I'm going to go back from component form to magnitude and direction. So I can sketch it, 71 for I and 217 for J. And I want this part right here. It's called the magnitude. It's a Pythag. 217 squared plus 71 squared. The square root of that is going to be close to 228 pounds. And then to get the angle, it's an inverse tan, always the J part over the I part. Tan inverse, 217 over 71. Will give me the angle of 72 degrees. So I'm going to go way back here at the beginning and draw that one vector where I just had 3. And I'll zero in on that in case we're getting too far back. Alright, so here where I had my 3 vectors originally, the force vectors acting on the spot, I'm going to replace them with one vector, and it's going to be a 228 pound vector. So 228 at 72 degrees. So 72 somewhere in here, and 228 is there. So assuming that that angle is 72 degrees, and 228 pounds. So putting it all together, that one vector, the purple one right here, will do the same as all 3 of these force vectors. Alright, so that's about it for tonight. We are going to be doing practical problems like these for a while. So we will close it down and hope you're having a good night. Till tomorrow. See you then.